Welcome to the Everyday Why channel, where we uncover the hidden logic behind the things you see every single day, but rarely question. Simple stories, clear explanations, no jargon. Picture this. Next time you're standing at a railway crossing waiting for a train to pass, just look down at the tracks. You'll notice thousands of sharp, jagged stones distributed across the ground.
Yeah, you see them absolutely everywhere.
Right. And for an audience familiar with basic infrastructure, the question isn't just, why engineers use loose rocks instead of a continuous concrete slab.
Right. It's really about how this highly specific geological arrangement is the only thing preventing a catastrophic failure.
Exactly. So today, we're unpacking the engineering specs to understand how these highly calibrated stones keep the world's heaviest machines from sinking, sliding, or derailing.
Because the engineering challenge really begins with the sheer scale of the dynamic loads here. I mean, a modern freight train can easily weigh over 10,000 tons.
That is a staggering amount of weight.
It really is. That generates an immense degree of downward pressure and severe harmonic vibration. If engineers just laid tracks directly onto bare soil or compacted earth...
The rails would suffer immediate subgrade failure.
Exactly. They would bend and just sink right into the ground.
Yeah.
So to prevent that, the rails are attached to perpendicular ties.
What the industry calls sleepers.
Yeah, sleepers. And those are embedded in that specific layer of stone, which is known as ballast. The ballast distributes the massive load, anchoring the sleepers to maintain precise track geometry under high-speed stress.
Looking at the material specifications for that ballast, it's clear they don't just, dump any available rock along the line.
Oh, no. They specifically require a highly angular aggregate, usually crushed granite or trap rock.
Right, so it's incredibly sharp and jagged.
Exactly.
Why does the mineral hardness and that specific angular geometry matter so much more than just the sheer mass of the rocks?
It comes down to friction and structural integrity. Smooth river rocks would simply slip and roll over one another under the immense weight of a passing locomotive.
Which would cause the tracks to spread apart.
Precisely. Instead, those sharp, jagged edges allow the crushed granite to interlock, forming a rigid three-dimensional matrix. Specialized heavy machines called tampers actually drive vibrating tines into the rocks to aggressively pack them together.
Wow.
And once they interlock, they perform two vital functions. First, they hold the sleepers in a vice grip. Second, they act as a massive dynamic shock absorber to dissipate those intense vibrations before they can shatter the steel rails.
So the granite needs that high mineral hardness so it doesn't just pulverize into dust under the constant mechanical friction.
Spot on.
That structural matrix makes perfect sense for downward pressure and vibration. But what about environmental factors?
Like water.
Yeah, if you have thousands of tons of steel resting on a loose rock bed, wouldn't a heavy rainstorm create severe hydrostatic pressure?
You would think so.
I'd imagine the ground underneath could easily erode or turn into a mud pit, compromising the entire line.
And that is exactly what would happen with an impermeable surface, like a solid concrete slab.
Oh, because it's prone to pooling.
Exactly. Pooling and subgrade erosion. But the ballast actually solves this by functioning as a high-capacity drainage system. Because of the irregular gaps between the angular stones, the interlocking matrix is highly porous.
Rainwater just filters through.
Almost instantly. It keeps the underlying subgrade completely dry and maintains the necessary structural friction.
Okay, so the porosity handles the water pressure. But does that thick layer of crushed rock also serve a purpose regarding the surrounding ecosystem?
How do you mean?
Well, keeping vegetation out of the track seems like it would be a constant, highly expensive battle.
It is a critical defense mechanism. The depth and density of the ballast create a highly hostile environment for plant life. It essentially acts as an impenetrable shield.
So roots can't take hold.
Right. If weed or tree roots were allowed to anchor into the subgrade beneath the rails, they would introduce moisture and physically heave the tracks out of alignment.
The stone deprives seeds of the soil and moisture they need to germinate,
keeping the path completely clear.
It's fascinating how a static pile of rocks addresses so many dynamic engineering problems.
Yeah, it really is.
But replacing it all with a permanent concrete foundation still seems like it would require less maintenance over time. Why do railway engineers strictly adhere to using loose aggregate?
The ultimate advantage of loose aggregate over a rigid concrete slab is microflexibility. The Earth's crust is never truly static. It constantly shifts, settles, and experiences thermal expansion.
Right, the ground is always moving.
Exactly. If you use a rigid concrete slab, any geological movement cracks the foundation, which leads to catastrophic track misalignment.
Ah.
Because the ballast is a loose matrix, maintenance crews can easily lift the tracks and pack more stone underneath to make precise millimeter-level adjustments.
That built-in flexibility prevents derailments when the earth inevitably moves.
It does, and it leaves you with a profound realization. We live in an era dominated by advanced LiDAR sensors, artificial intelligence, and cutting-edge logistics. Yet, the absolute safety and viability of these massive high-speed machines rely entirely on the physics of crushed, jagged rocks.
That is wild to think about.
It really prompts the question, what other ancient, seemingly low-tech solutions are quietly holding the rest of our modern infrastructure together?
If you enjoyed this story, hit the like button and subscribe to the channel for more everyday mysteries explained simply. See you in the next one.